All right, let's take a look. What is the entropy of 100 molecules in a system that consists of 1, 2, 3, 10,000 boxes? Couple things to be careful about here is, first of all, they randomize this problem. Your number of boxes is going to be different, your number of molecules is going to be different. So don't think you can take this answer and plug it in directly. All right, let's take a look. Well, we know according to the Boltzmann distribution, the Boltzmann theory of entropy, that entropy is equal to a constant times the natural log of the number of ways the system can be arranged. In a gaseous box, we define the number of ways a system can be arranged as the number of boxes raised to the number of molecules. So for our system here, we have the natural log of, and I'm going to make this a little bit easier here. We have the natural log of 10 to the 1, 2, 3, 4, 10 to the 4th. So we got 10 to the 4th raised to 100 for a number of ways things can be arranged. Now, the first thing you're going to say is when I try to put this into my calculator, that I get this big old calculator error because my calculator can't take raising something to the 100. Well, that's where some algebra comes in. The natural log of x to the a power happens to be equal to a times the natural log of x. So I can actually come over here and I can say, I can say that I'm going to take this 100 here and I'm going to move it outside my logarithm. So I'm going to have k times 100 times the natural log of 10,000. Now we have something our calculator can handle. I can never remember a value for the Boltzmann, but I always remember how it's derived. And that's the gas constant, 8.314 times 10 to the negative third kilojoules divided by Avogadro's number. And I am just like unbelievably sloppy there. Let me clean that up a little bit. The joys of writing with stylus. So I'm grabbing my calculator. I'm going to resolve the terms on the outside first. I've got 8.314 exponent negative 3 divided by 6.022 exponent 23. So I've got S is equal to 1.3806 times 10 to the negative 26 times 100 times the natural log. Whoops, where did my natural log button go? There it is. Times the natural log of calculator issues here. Bear with me, please. So I changed my log into a 9.21. Now I'm going to multiply everything through, and that's going to give me it's going to give me 1.27 16 times 10 to the negative 23rd, and that's going to be in units of kilojoules and that's going to be in units of kilojoules. So we want to make sure that we're aware of that, because they often ask us in joules to put census entropy. They'll often ask us to put it in joules. If they do ask us to put it in joules, remember all right, that's it. Real quickly, I'm getting a little sloppy here. Kilojoules per Kelvin, and that goes back to our gas constant here being kilojoules Kelvin mole. And it turns out your answer does prefer it in joules. But there's your answer, 1.27 times 10 to the negative 20th joules.